So finally we'll touch upon some problems from the source follower. Okay, source follower or buffer, or voltage control voltage source, all these things are one and the same. Okay, so this is question number 5 that we want to discuss. Okay, so before going into that, let's just briefly discuss what is a source follower. We have done it already, but then it's just a recap. Okay, so you have an input given to the transistor, and then the drain is connected to bias voltage, and the output is taken at the source, with the load RL. Okay, this is essentially the source follower. And then incremental picture is something like this: V in, and you have an incremental current of GM V in minus Vs, because this S is not grounded. This is your V out. Okay, and which V in minus V out you can say, and then you have RL here. Okay, and this is essentially the V out, and this point drain voltage is grounded. Okay, so this is the source follower, and of course you will have a gain of GM RL by 1 plus GM RL. Okay, you can work it out yourself. We have done this multiple times, and this is the gain, right? Now you can write down this gain as we did for the common source with source degeneration. You can take GM common outside. Okay, and then you can have RL divided by 1 over GM plus RL. Okay, this is the gain. Now you see, as I said earlier, numerator will have the load resistance. Okay, so there is no change in that. And the denominator, I said that you will have that particular value of the resistances that you will see when you look into it from the source. I said source there because that was the common terminal. Here it should be drain because the drain is a common terminal. And looking in this side, you see I have this resistance due to this component as well as the RL itself. Okay, so both the components I have looking into the common terminal. Here the common terminal is the drain. So looking into this side, I have 1 over GM of this transistor as well as the RL. Because why I see RL again here, because it is the output. It is basically the output of the MOS transistor, which is at the source terminal, is also common to the input, and that is why you see RL here as well as for the GM. Okay, so in the previous case you looked into the source terminal, and there you just could see only the 1 over GM of the transistor or whatever RS was connected to the source, but now you are looking into the drain, you see 1 over GM of the transistor as well as RL. Okay, so you have that in the denominator. So from this you can see the circuits by inspection and write down the gain as such. Okay, so if I give you a circuit like this, say I have a transistor, NMOS transistor, where I have some V in, and of course some V bias is there, V bias plus V in, and this is where I take my output. And then say I have again a PMOS transistor whose drain and gate are shorted and connected to ground. So of course you know that this will have a resistance of 1 over GM, right? And then you know how to put down your gain. Gain is nothing but, first of all, this is going to be a load now. So this is 1 over GM resistance. So load 1 over GM, let's call it M1 and let's call it M2. So this is 1 over GM2. So 1 over GM2 divided by, so looking into the drain side, I have 1 over GM1 of this transistor plus 1 over GM2 again. So whatever you see here will also come in the denominator, plus the GM1 of the transistor that is seen from the gate side. Okay, so this is going to be the gain of a source follower. Okay, so this is very simple things now on, because you see the circuit, you write down from inspection what should be the gain. Okay, because the idea, the concept is something that is clear to us from the previous lecture, and we are trying to make use of the circuit tricks to come up with the answer immediately. Okay, so these kind of things will be useful for you for your gate examinations and any other competitive examinations and so on. Okay, So question number 6, let us take a case that we have kind of done already. Okay, so let's take this case. So we have done this already, like VDD and the PMOS transistor, let's call it M2, whose gate and drain are shorted, and let's take an NMOS transistor with Vin. Okay, and then let's take the Vout at this point. Remember, this is basically, this is not a source follower essentially. Let me say this is my bias picture, some C1 which is an infinite capacitor and all these things. Okay, so this is not a source follower. Okay, this is some other question, I am relating it to something else. Okay, so this one you see that this is essentially a common source amplifier, and you have taken the output at the drain and you have a current mirror load, I'm sorry, a diode connected load. Okay, so how do you solve it? It's very straightforward, whatever we have seen. So this one will be a short incrementally, and this will offer a resistance of 1 over GM2, and this is having a GM of GM1. So this is just like a common source amplifier with a load of 1 over GM2. So the gain V out by V in is equal to minus GM1 times 1 over GM2, which will be GM1 by GM2. Okay, so we didn't do any kind of solution, we just saw the circuit and wrote down the answer because we have done initial analysis earlier. Okay, now if I have another situation, let's say question number 7, say I have the same circuit, I'll draw it here. Okay, the same circuit, I'll draw it here. Let it be an infinite capacitor and same current, and let it have a GM1 transconductance. This transistor M1, transistor M2, let it have a transconductance of 1 over GM, transconductance GM2, it will offer a series resistance of 1 over GM2, and let the Vout be here. Okay, now on the input side, except for giving the signal directly here, let me choose my signal to come from another stage. Okay, so let me draw the previous stage. So let me put the signal here and let it be biased in this way, and let the output come from here. Okay, so now let me call it M0. So for this circuit, what will be the gain? Okay, see that this particular part is exactly same as this one, only addition is this particular transistor. And you know that if this transistor is maintained in saturation, then you will have GM times this resistor divided by 1 plus GM times this resistor, and this resistor is going to be infinity, right? So you are going to have a gain of 1. So if you supply V in here, you will get V in here also, and once you have V in here, the same analysis will apply and the gain will be exactly same as what you had in the previous stage, minus GM1 by GM2. Okay, so you try to look at the circuit. See, the reason for me to give these two problems is that when you look at circuits with more than one transistor, you do not panic. Okay, here this is very straightforward. This you could actually relate to the case where you had this situation which you had solved earlier. Okay, this is VDD, this is ground, this is a V out, and this is V in. Okay, you had solved this earlier, and then you know that this is 1 over GM2 and this is GM1, or so GM1 times 1 over GM2 will be your gain. So you got this answer. Now because the current source is there, doesn't matter because incrementally it is short. But here the same scenario here, except for one transistor is added here, and intuitively you see that this is a source follower because input is given at the gate and output is taken at the source. So it's source follower, which will have a gain of unity because you have a current source here which will offer a resistance of infinite resistance. You put RL is equal to infinity here, you will have AV is equal to 1. Okay, so if the gain is 1, then Vin will appear here also. Then after, it is very straightforward. You already done it, and though you will get a gain of minus gm1 by gm2. Okay, so this is the way you approach circuits and solve the problem, so that you get quick answers, and also there are more or less accurate answers. In a sense, you have done approximations, but then that is okay for hand calculations. Okay, so let's see another question. Let's take a circuit like this. V out, VDD, V bias, some bias is applied, another PMOS transistor where I give some bias plus some input. Okay, and output is taken here, and this is my RD. Okay, so you see, of course, this is essentially a common drain stage. Okay, because input is given at the gate, output is taken at the source, which is given to the next stage where input is given at the source, output is taken at the drain. Okay, so it is a common gate stage. Okay, so what will be the answer of this one? You can see this and write by inspection that this transistor will have a GM of 1 over GM1, let's call it M1, let's call it M2, and this will have a GM of 1 over GM2. Okay, so you will have RD, because output is taken at the drain, so it doesn't matter to include, you just look at things from the, it's a common drain stage, right? So you look at it from the drain side. So you will see that RD is in the denominator, and in the RD is in the numerator, and in the denominator you can put 1 over GM1 plus 1 over GM2 series resistances. Okay, so see, you can always work it out and see if it is right or not. So I will also work it out just for this problem. So I have Vin applied here. V bias anyway is grounded incrementally, and then I have a current of GM times Vin, okay, from drain to source. Okay, this is the drain and this is the source. Now see, my drain is basically grounded, so this is my drain, so GM times is in this direction, upward direction. Okay, GM times Vin, because see, although from source to drain I have my DC current, as far as the PMOS or NMOS is concerned, incrementally they are the same. So incremental current always flows from drain to source, and PMOS drain is connected to ground, so drain I have grounded it. Okay, so from drain to source, this is the source terminal, I have a current that is flowing, which is GM times VSG. Okay, sorry, GM times VGS. So VG is Vin and S is anyway this terminal, let's call it VS2. Okay, so VS2, Gn times GM1 times Vn minus VS2, and you have another current flowing from drain to source again, from the top to bottom. Okay, and this current will have a DC bias anyway, is grounded, so it is 0 volt, will have a value of GM2 times VG minus VS. So here it's going to be just minus VS2. Okay, or you can say GM times VS2 flowing in the upward direction, and it's going to a load of RD. Okay, this is my output node, V out. Now you see, it is straightforward. Whatever current you have here is the same current that is flowing in this direction also. Okay, so whatever current that is coming in this transistor is the current that is flowing in this transistor, which is the current that is flowing into the RD, right? There is nothing that is different. So GM times VS2 so GM2, so this is GM2 times VS2 is equal to GM1 times Vn minus VS2. So from here one can obtain VS2 as Vn multiplied by GM1 divided by gm1 plus gm2. Okay, so gm times this quantity is flowing through rd, so my av is going to be gm2 gm1 times rd divided by gm1 plus gm2, and this parallel combination I can always write it as rd divided by 1 over gm1 plus 1 over gm2. Okay, so this is what my gain will be. Remember, all these problems that I am calculating, I am not considering any kind of R1 R2 voltage divider bias or any kind of bias resistors. I am just considering whatever is necessary. So these are all ideal cases. There can be always cases with bias resistors, there things can vary, but once you look at a circuit, seeing by intuition, you should be able to say what will be the maximum gain. That is the idea. Okay, finally question number 9, we'll wind up with this. We'll look at a case of cascode amplifiers. Okay, so you have RD, VD, 2 transistors. Of course, this is a cascode, so some bias is there, some VN is applied, plus some bias is there. Okay, and let's say this is an NMOS transistor, and this is also an NMOS transistor, and this is, let's say, a common source stage, and this is a common gate stage, because this output is given to the input here, and this is where you will take the V out. Okay, remember the difference between these two questions is it's a cascode stage because common source connected to common gate. Okay, so it's a cascode logic. Now what will be the answer? Okay, what will be the gain? So definitely it is not going to be same as that of this one. It will be certainly different, because this technique will not apply to a cascode logic where you connect a common source and a common gate. Okay, so in this case you will have to work it out the problem, because I just wanted to illustrate the fact that you cannot blindly go and apply this technique to all circuits. So the techniques, it's is possible only when you have the situation that I said, like you have a common source amplifier with source degeneration or a source follower, or things like that. Then only you can apply the technique whatever we have discussed, right? So once you go through this video again and again and you solve problems on your own and apply those techniques, you will get used to it and you will have your own intuition on circuits. Okay, so now if this is the case, we have done this earlier. I mean, we have done this when we illustrated the cascode amplifiers, but then let me pose a new situation that, say I have one more resistor RP here. Okay, so when this RP is infinity, or when RP was not zero, when RP was not there, if it is absent, we said that this is a voltage, so it's a common source amplifier, which is a voltage control current source, and this is a current control current source. This just passes the same current, right? So we said whatever current that will be the output of this transistor will be the same current at this point. So we said that the gain will be exactly same as minus GM1 times RD. This is what we said. In fact, you got an expression like minus GM1 times GM2 divided by GM2 times RD. Okay, this is what you get if RP is infinity. Okay, now if RP is not infinity, let's see what happens. If RP is finite, okay, then let's see what will be the answer. So again, let's go with the incremental analysis. So if you put down the incremental picture, so I have some Vn applied here, and I have a current source of value GM1 times Vn, and of course I have RP here, and I have another current source of value GM2 times Vs2, where this node is Vs2. Okay, and I have an output V out here and RD appearing here. Okay, so I have this relevant node where I can write KCL. I have 3 currents flowing in, and I have this node where I can take the output voltage. So if I do that, then my V out by V in, what I would get, see, you can solve the circuit and get it for yourself. Then the V out by V in, I would get as minus GM1 times GM2 times RD, okay, divided by gm2 plus 1 by rp. Okay, so you see, if rp was not there, this is the expression. If rp is there, I have 1 over rp being added to the see, essentially this is having a transconductance of gm2. Okay, sorry, this is having a transconductance of gm2, and this one is having a transconductance of gm1. So you had this gm2 in the denominator here. Now along with the gm2, I have 1 over rp being added in parallel. Okay, I mean they are basically added, but when you add two transconductances, this means they are in parallel. Okay, that is how it is being arrived. But then you can keep this result in your mind, and you see that if you have an rp added to a particular node on a cascode stage, then you will have that particular resistor. Okay, some rp, some parasitic resistor. So this resistor will occur in addition to the denominator. That is what the change you will see. Okay, so these are all some basic circuits with some small changes, and you see how the results will vary, and it would be useful for you to build up some intuition and come up with an answer in the examinations or some competitive exams. Okay, so let's wind up the problem solving sessions, and if you have any further questions, we can always take it offline.